Let's talk about inductors in an AC circuit. So just an inductor by itself, assuming there's no capacitance or resistance. Recall an inductor is a coil of sorts that opposes the change in current flow. So I pulled in the equations from our test notes for the inductor. We know that the voltage drop across an inductor is directly related to the inductance of the inductor and the rate at which the current, so the current in the circuit is changing. Now, our source is changing with time. So maximum source voltage. We've been using cosine to describe our voltage. I'm going to continue with that. If the inductor is the only element in this circuit, then the inductor's voltage at any given moment in time has to equal the source voltage as well. And that's from Kirchhoff's loop rule. Kirchhoff's loop rule still totally must apply. So that means we're going to say the potential difference across the inductor as a function of time, which our author is using this lowercase v to represent, will be a cosine function. So capital V sub L represents the maximum value of the potential difference across the inductor. So the amplitude. But we know this is equal to L di dt. We're using a subscript L on the current as well, since this is the current in the circuit with just the inductor. To get to our current, if we rewrite, as shown up here, the di is equal to essentially we're dividing by L and then multiplying the dt up. It turns out we can integrate to find the current equation. So we divide by L, we still have the cosine function, we have dt now. We're going to integrate with respect to time. Now, I know the derivative of sine gives me cosine. So if I want to say that we get to sine omega t by integrating, then I need the omega cosine omega t to represent the derivative of sine omega t. So that leaves me still with the VL, so the maximum voltage drop across the inductor, divided by omega L. We are going to leave our current like this, so we are making the assumption that the current through the inductor at time equals 0 is 0. So if you recall when we talked about inductors originally, we said the inductor is always opposing the current, and so essentially it controls how quickly the current can change. So we're making that same assumption here. We're starting with that assumption that the current through the inductor before the circuit was hooked up was 0. And under that assumption, as the voltage drop across the inductor is described as a cosine function, the current will be described as a sine function. So if we were to graph the voltage across the inductor as a cosine function, then the current will be a sine. So it will be a peak when the voltage is 0, when the voltage is a maximum, both a maximum negative value or a maximum positive value, the current is 0. So here it would be its peak again, here it will be 0 again, here it's going to be a peak. So we get a sine function describing the current. Now, we had a similar situation with the capacitor, but with the capacitor, the current was ahead of the voltage by 90 degrees, or pi-half radians. With the inductor, the voltage leads the current by 90 degrees, or pi-half radians, which is explained in the sentence above these equations. Again, that's going to be important in terms of drawing a phasor diagram. If we were drawing a phasor diagram at a moment in time where the phasor representing the maximum voltage, the value of the voltage at that moment would be this positive x component. But if the voltage is leading the current, that means we have to draw the current phasor, meaning the maximum value of the current behind the voltage phasor by 90 degrees. So when we put a resistor, inductor, and capacitor together and talk about a series circuit, this is going to come into play in determining how everything works together to allow the flow of current. Now, in terms of our current equation, this VL over omega L must represent the peak or maximum value of the current that can flow in this circuit. It's the amplitude of the function. Since the function is describing the current, then the amplitude represents the peak or maximum value of the current. If I bring the omega L portion over and recall that volts is equal to amps times ohms, this quantity, omega L, must have units of ohms. We call this the inductive reactance. Excuse me. We have an X sub L is equal to omega L. This has units of ohms, meaning this is how the inductor affects the current flow in the circuit. The maximum voltage across the inductor would be the maximum current times this inductive reactance. So as XL changes, so does this current. And XL changes based off of not only the inductor value, the inductance L, but also omega. This omega in here, if we come back to the source, it is the omega, the angular frequency of the voltage source. So just by changing the source voltage, the frequency at which it's oscillating at, that will affect how much current can flow in the circuit. Now, if you recall a capacitor, so over on the side here, with the capacitor, we found X sub C was 1 over omega C. There was an inverse relationship between the angular frequency and the capacitive reactance. As omega got bigger, X sub C got smaller. The inductor is opposite. As omega gets bigger, X sub L gets bigger. So XC and XL, the capacitor and inductor, affect the current flow based off of not just their capacitance or inductance, but also the angular frequency at which the source is oscillating at. But they behave differently. As one gets bigger with angular frequency, the other gets smaller. So we're going to look, and by the way, really quick, all of these equations are right here. This is directly from the test notes. this is just solved for current instead of the way I wrote it in terms of voltage is equal to current times reactance. So you have these main equations. We can have a set of equations that describe and relate these maximum values together. What we're going to look at next is a series circuit that has all three, a resistor, an inductor, and a capacitor in series. And to look and determine how much current can flow, that will depend on the angular frequency as well as the values of XL and XC and R.